Hey guys, welcome back to my channel. Today we are going to learn about AVL tree. Before we dig deep into AVL trees, let's recap our understanding of binary search tree. A binary search tree is a tree in which all the nodes follow the following property, which is the left subtree of a node is less than or equal to its parent node. If you see 6 is less than 10, 4 is less than 6, and the right subtree of a node is greater than to its parent node, which is 18 is greater than 10, 21 is greater than 18. Now 15 here is greater than 10 but less than 18. 8 here is less than 8, 10 and greater than 6. Now I hope you remember this. If not, please go to my binary search tree video and try to understand it. Now let's learn a little bit more. Let's take a simple example where the input numbers we give just 3 numbers as input, and let's try to construct a BST with the previously known rules which we defined here. Let's say the input number is 10, so we insert a number 10, then 20 which is greater than 10, so we put it to the right side, and then we get 30, we put it to the right side of 20. Now this is one of the structure. Now let's change the order of the numbers. Let's make it 10, 30 and 20. Then 10 will be the root node, 30 will be inserted to the right side of it, and 20 to the left side of 30. Now this is another structure. Now let's take 20, 30, 10, then you know how it gets created. Then 20, 10, 30, these two are getting the same structure. Then 30, 10, 20. Now just a second, you get 30 first in the root node, and then to the left it is 10, and to the right side of it would be 20. Then let's see the structure 6, which is 30, 20 and 10, which will be 30, which is the root node, 20 to the left side of it and 10 to the right side of left side of it. Now let's say you have these 6 structures, or probably 5 structures because one is the same. If you are asked to find a number, let's say 30 for example, what is the time complexity of this particular tree? Now if you are supposed to find the number 30 which is residing in the last or the leaf node of this particular tree, you will have to go over all the elements. This is as good as a linear search. Whereas here you just have to do a single hop, even here single hop, and so on. Now what are we trying to understand here? What we are trying to identify here is searching of an element in a BST depends on the height of a tree. It can be log n, it can be n. Basically this particular thing is defined by the height of the tree and the order of your input, which is coming as seen in this example. Let's say 10, 20, 30, you construct this kind of a tree, 10, 30, 20, you construct this kind of a tree, and so on. Now, as we discussed, when we are supposed to find 30 in the structure 1, we actually took comparison of n elements, which is n being number of elements, which is 3 in our use case. Now that is where AVL tree comes into picture. AVL tree is nothing but a binary search tree, but there is a property which is the difference of heights of its left and right subtree is less than or equal to 1, and it can even be 0. It can be either 0 or less than or equal to 1. which is -1 and +1. This we call as balance factor, which we will try to uh, understand in the next couple of videos. This technique of balancing was developed by Alderson, Welsky and Landy. That is the reason it was called AVL. I hope you understand this piece. In the next couple of videos, we will try to understand what balance factor is, what LL rotation, LR rotation, RR rotation, RL rotation is. I hope you learned something new in this video. If you did, please do like, share and subscribe to my channel. Thank you.